In the last video, we went over just a basic application of the area bounded by a polar curve. In this one, I want to try and find an application that's a bit more fun. We're going to use this formula, this integral formula that we have, and we're going to go back and we're going to prove that the area of a circle, the perimeter of a circle is in fact 2 pi r. Okay, let's see how we're going to go about doing this. Let me construct just a general circle on the graph that we see here. So we're just going to have a circle. Hopefully it corrects. Okay, so the origin's not perfect, but you get the general idea. Let me just move the circle to the origin. There we go. So the point of our math was, or the point of this drawing was to essentially model what we think a circle looks like, or what it actually does look like. So it's going to start at 0 radians, our graph. We're going to start at 0, and then it's going to go all the way around, and then it's going to end. It's going to end at 2 pi. So theta, our theta bounds are going to be between 0 and 2 pi. And our r function for the distance is just going to be some constants. Let's define this as big R. It's just going to be some constant because as you can see, it's not varying dependent on the theta. It's just always a constant length away. This is going to be big R. This is going to be big R. So it's just varying by a constant length away from the origin. Okay, now that we have all of this set up, we can essentially just plug this into our formula. So let me go to the side here actually. And let me just zoom out. Okay. So we can set up our area. Let me just use a different color. We can set up our area our area formula to basically look like this. So we're starting from 0, then our bound ends at 2 pi over here. So we're going up until 2 pi. And then our formula was 1/2 r squared d theta. Now this is where it becomes interesting. Because r isn't dependent on theta and it's just a constant big R, we can pull this entire thing out. So it becomes 1/2 and r just becomes big R. So that just becomes big R squared. It just becomes from 0 to 2 pi of d theta. And now we can just treat this as, any integral. We just get 1/2 r squared, and evaluating this would just give us theta evaluated at, there should not be a line through there, 0 and 2 pi. So what does this yield us? We then get 1/2 r squared into 2 pi minus 0. Once again, I put a line there. Should be no line through that 0. That's just a 0, not a theta. So 2 pi minus 0 is just 2 pi. The 2's cancel out, so we get pi big R squared. Now, this should remind you of the formula of a circle, which is pi r squared. And remember, this big R is our radius because it is just the distance measured from the origin to this point on the circle. So using our formula right here, we've successfully proved the area of a circle. Now that's pretty neat in my opinion. That's a pretty cool application of this problem of just using polar graphs and finding the area bounded by polar graphs. Alright, I'll see you in the next video.